Okay, this is part 2 of our lecture. We didn't finish this as the bell was ringing, so I wanted to finish this up quickly so you have a good demonstration of a function as harmonic. We need to show, again, this is problem number 76 on page 995. Number 76, page 995. Show the function 1 over the square root of x squared plus y squared plus z squared is harmonic. Now that is, we needed to show it obeyed or satisfied Laplace's equation, which meant that the Laplacian of this particular function works out to be 0. That's the task. Show that, and then we're done. For your problems that you're going to be doing at home, I've got various functions. For example, number 1, you needed to show that the Laplacian of x squared plus y squared minus 2z is equal to 0. That's what you need to show. That was fairly straightforward. Now remember, what this Laplacian is asking you to do is to take the second partial with respect to x or whatever the function is. Add to that the second partial with respect to y of the function, and then add to that the second partial with respect to z of the function. And if you take those 3 second partials and add them up and you get 0 as a scalar, then this is in fact a harmonic function. The notation is sort of weird. Remember, the gradient was a vector operator. So you can sort of think of it as partial with respect to x, partial with respect to y, partial with respect to z as a vector, and you operated it on a function, you ended up with a vector. So what do we mean by del squared? Right, this is the gradient squared. And you can think of this as a vector dotted with a vector. So if you just go back and think dot products, so say we had partial with respect to x, comma, partial with respect to y, comma, partial with respect to z, dotted with the same thing. Well, none of these are real vectors, but we're sort of thinking like they were, and now we're thinking dot product. And just remember how dot product worked. You took and you multiplied these two together, and then you multiplied these two together, and you multiplied these two together, and you added them all up. So that's sort of where this notation comes from. It's like partial with respect times the partial with respect to x is the second partial with respect to x. And then partial with respect to y times partial with respect to y is the second partial with respect to y. We're adding them all up. Okay, so that's sort of what we're doing. What we need to do in our case is to show that those 3 seconds add up to 0, right? Now, on the homework, this is the first one, and because, it's, I don't want to scare you, the homework is designed to be pretty easy. Let's look at this guy just for a second. I'll do the first part of your homework for you. So, partial with respect to x of this function is 2x, and the second partial with respect to x of this function is what, 2, right? So you can sort of do that in your head. And then the with respect to y, so let's do the same thing. First partial with respect to y of the function is 2y, and the first partial, or the second partial with respect to y would be 2. So far, those are the first 2. And then the third, I guess I got to copy the problem down, right? Okay, and then the third second partial we have to do is the partial with respect to z. So we could do that. Let's see, the partial with respect to z of f works out to be minus 4z. And so the second partial with respect to x, or with respect to z, second partial with respect to z of f works out to be minus 4. And then you add these three things up. You add this, this, and this. And sure enough, 2 plus 2 minus 4 adds up to 0. That makes this particular function a harmonic function. So it's a task of finding 6 partial derivatives. 3 first partials, 3 second partials, add them all up. If you get 0, then you're done. Okay, so here's the problem in the book. And all we have to do is find those partials, and we've already done some of this work. So let's sort of recall what we did. The first partial with respect to x of this particular 1 over f function, this 1 over the square root of x squared plus y squared plus z squared. Go back and look at the previous little video, and you'll realize that that came all the way out to, after we cleaned it all up, as minus x, right? It was minus x over x squared plus y squared plus z squared to the 3/2. That's what we got. Now, we were going to have to take the partial of this to get our second partial. I suppose I could use the quotient rule. It wouldn't be too terribly bad. But instead, I want to use the product rule. So I'm going to rewrite this as minus x times x squared plus y squared plus z squared to the minus 3/2. So when I take the second partial, I can get it a little bit easier, I think. Because I can just use the product rule. Okay, so we're differentiating this thing, right? That's the first partial. We're differentiating that with respect to x, and I see a product right off the bat. Okay, so the derivative of a product is the derivative of the first times the second, x squared plus y squared plus z squared to the minus 3/2. Okay, plus the first, which is minus x. I guess I could just write minus instead of plus a minus. Plus the first times the derivative of the second. So what do we have? We have minus 3/2, and then we have this sum of squares again. So now we have to subtract 1 minus 3/2, and then take the derivative of the inside with respect to x, and that's 2x. Okay, so there's the second partial. And we're going to have to do that again, the first partial with respect to y, first partial with respect to z, and then take the second partial with respect to y, second partial with respect to z. They're all going to be done similarly. I think I want to clean this up quite a bit. It just looks terribly messy to me. So we can see the pattern more clearly. Second partial with respect to x of this 1 over f function. Remember, f was the magnitude of the vector field. Works out to be, what do we got? I lost minus sign here. Shame on me. Okay, so the derivative of the first should have been minus 1. That would have came back to haunt me. These two are positive, right? Minus minus is a plus, and these twos cancel here. Okay, so now I think I can clean it up. Yeah, if it didn't work out to be 0, there's obviously an arithmetic mistake somewhere. It says it is harmonic. Okay, so first term, we've got minus 1 over x squared plus y squared plus z squared to the minus, or to the positive 3/2 if I throw it back down in the denominator. And then for the second term, let me write it here. What do I have up top? I have an x and an x and a 3. So it looks like 3x squared. And then on the bottom, we have x squared plus y squared plus z squared to the positive 3/2. That's not right either, Joe. Oh, I said I was going to start. So it's been a long week, sorry. Minus 5/2. And all you're chuckling going, yep. Minus 5/2. So down in the denominator, this is a positive 5/2. Okay, and I'd like to add these two fractions up just to get a single fraction. So I can do that by multiplying this first term by x squared plus y squared plus z squared, x squared plus y squared plus z squared, because then I'll have this to the 3/2, this is to the first, and that will be to the 5/2. Okay, so hopefully you can follow that. Let's see, here's my second partial with respect to x of 1 over f. I have a minus x squared minus y squared minus z squared plus 3x all over x squared plus y squared plus z squared to the 5/2 now. Yeehaw. Okay. Now, because of the symmetry of the situation, I could almost immediately, you might want to go in and just verify this yourself, that when I find the second partial with respect to y and the second partial with respect to z, I'm going to get almost the same structure. The only difference is when I do it with respect to y, minus x squared minus y squared minus z squared, I'll have 3 y's here. Denominator is still the same. And when I take the second partial with respect to z, minus x squared minus y squared minus z squared, screw it up again, Joe, 3x squared. I know what I'm supposed to get in the end. That's the frustrating thing here. So as I'm going through this process, I'm sort of jumping ahead, but that's okay. X squared plus y squared plus z squared to the 5/2. Okay, now the Laplacian, the harmonic function idea, says if I take this second partial and this second partial and this second partial and add them all up, I get 0. Well, in order for, they all have the same denominator, so that's easy. All I have to do is look at the numerators, make sure when I add the numerators up, I'm going to get 0. And it's pretty obvious, I hope, that this is minus, that bit right there is minus x squared plus y squared plus z squared. And we have it again here, so that's 2 of them. We have it again here, so that's 3 of them. So those green guys are minus 3 of those. And if we just look at the other terms, there's 3x squares and there's 3y squares. We're adding these up, and 3z squares. So that's 3x squared plus y squared plus z squared. And sure enough, that sum is 0. Okay? Now, notice on the graded homework, I said, do all your scrap work off to the side and then give me a clean copy. It will take a page or 2. Some of the second partials are tedious. I don't think any are quite as tedious as this example. This is a hard problem. The ones on the graded homework are much, much easier. Certainly the polynomials you'll do in a heartbeat. But even when you get down to the log or the arctan, as long as you remember how to take the derivative of an arctangent, right? Y is arc tan of ugly, then the derivative was 1 over 1 plus ugly squared times the derivative of the ugly, right? As long as you remember that. And I think we've done enough logs here. Okay, there. This should not be a difficult graded homework. Okay, let me stop this guy here and have fun over the weekend.